All right, let's briefly go over some of the ideas that we have covered in this chapter and in this course so far. So here they are. We started by establishing a relationship between a function and its inverse, understanding how the input output can be interchanged to find either of them. Specifically, f of f inverse equals f inverse of f equals x. Then we saw the condition for the existence of an inverse, which is that a function has to be 1 to 1. We found two ways of finding the inverse, A graphically and B algebraically. We looked at properties of exponential function. Um, Here's a brief, some of the important properties are briefly mentioned here. We looked at the natural exponential function, e to the power x, its definition, its graph, its derivative, which is itself, and thus by definition, its antiderivative, which is also itself plus a constant. Then, since we've learned a new function, we also learned its inverse, which is logarithm, which has the following property, um, which you can derive just from the properties of the exponent. We saw the derivative of the log function is the 1 over x function, consequently, which means that the antiderivative of 1 over x is the log of absolute value of x plus c. We model exponential growth, which is any um, quantity that is changing proportional to its initial amount. So dp over dt equals k times p. When you solve this differential equation, it comes out to lambda times e to the power kt, where lambda is p0, which is the value of p at time 0. The next class of functions we looked at was inverse trigonometric functions. We looked at the definition, graph, domain, range, and the derivatives of those functions. Hyperbolic function, the motivation being that they are similar to trigonometric function, their definition, graphs, domain, ranges, and their derivatives. Then we looked at inverse hyperbolic functions, their definition, graphs, domain, ranges, and derivative. And then evaluating limits of the form e to the x, where x goes to plus or minus infinity, and log x, where x goes to infinity, or x goes to 0 from the positive side. So basically infinite limits. 0 are infinite limits. Um, so here's the motivation for our next topic, which is you recall problem number 10 from homework 1, where you estimated e to the power x as being greater than or equal to 1 plus x. Well, let's try to do something similar with log x. So the hint for that problem, and some of you got the problem correct, is to use facts about increasing or monotonic function. So my claim is that log of x is less than negative 1 plus x for all x greater than 1. Let's add an equal to sign here. So I start by letting f of x be log x plus 1 minus x. I look at f prime x as 1 over x minus 1, which is always less than equal to 0 for x greater than equal to 1. Why? Well, when x is more than 1, 1 over x is less than 1, so it follows that it's negative. This means that this function is decreasing for x greater than equal to 1. Consequently, it means that f of x is less than or equal to f of 1. But what is f of 1? F of 1 is 0, and that gives us the inequality as required. Now what happens at 1? At 1, log of 1 is 0. We've seen that by definition. Now let's say from here, I kind of want to analyze the behavior of the ratio of these estimates. So I say f of x is log x over negative 1 plus x, and I want to understand what happens to this function. Now why? Why would we want to look at this function? One thing is that we're trying to estimate log of x with a linear function. And by looking at the ratio, we can check how good the estimate is, right? Because if the ratio increases, it means the estimate gets worse for higher values of x and so on. Now, obviously, f of 0 is not defined because, well, log of 0 is not defined. But what happens is limit as x goes to 0 for f of x. Um, let's see. I want to look at f of 1, not f of 0, and the limit as x goes to 1 of f of x, right? So I can rewrite this function as hx over gx, where hx is log x and gx is negative 1 plus x. By limit property, the limit gets distributed, and what I have is something very small divided by something very small. Now this kind of situation or this kind of quantity is called an indeterminate form, because we are not able to determine a value for it directly. Okay. So what happens is that when you have something small divided by something small, it's not necessarily zero, it's not necessarily infinity. It can take any value between zero and infinity. Now there are some more indeterminate forms. So for example, some non-examples first. If something is going to zero divided by constant, we can immediately conclude that this is zero. If it's a constant divided by something that's very large, then it's zero. Constant divided by something that's very small, it's either infinity or negative infinity. Something going to infinity divided by constant, it goes to infinity and so on. So these are not indeterminate terms because if you think about it a little bit, you can assign values. The two basic indeterminate forms are something really small divided by something really small, or something really large divided by something really large, right? Or approaching zero divided by zero, or and approaching infinity over approaching infinity. Let's look at an example of the second one. Say limit x squared minus x over x squared minus 1. Clearly, as numerator, as x goes to infinity, numerator goes to infinity and denominator goes to infinity. Now, some strategies to resolve these issues. Because these are algebraic terms, I can factor, right? I can factor the top as x times x minus 1 and the bottom using difference of squares as x minus 1 times x plus 1, which gives me 1 half. The problem term gets cancelled, so it no longer goes to infinity. Um, Actually, so I'm changing this to x goes to 1, numerator goes to 0, and the denominator goes to 0. So it's still a 0 by 0 case, not infinity by infinity. Now, you've seen this limit before. As x goes to 0 sine x over x, this limit is 1. This can be argued geometrically. It's a bonus problem. I'll submit an argument for this, and I'll post a video about it later in the week. And in the next video, I'll be looking at some specific situations and strategies to follow for assigning values to indeterminate forms.